Okay, so this is our process control project. We worked with a graduate student named Scott from the mechanical engineering department, and what we wanted to do was model a process for friction stir welding. So I'm Tyler Mayberry, we have John Housen and Michelle Chen. Okay, so the objective of the experiment, like I said, was to create a PI model for friction stir welding, and we had three variables that essentially affect the tool temperature, the first of which was spindle power. Also, we had the z-force, or the pressure in the z direction, and then also the velocity of the metal as it travels through the friction stir welder. And so in the next section we will outline the methods that we used to model those three variables and their effect on tool temperature. So what we wanted to do is we wanted to make one of them the manipulated variable per Scott's request. So we decided to make the spindle power the manipulated variable and treat the other two variables, z-force and x, direction velocity, as disturbances that were modeled in a feedforward controller. And so as we went through our experiment, we had 5-step tests that we received from Scott in Excel data, and we wanted to model those in an FOPDT model and find the tuning parameters tau, KP1, KP2, and KP3, where each of the KPs relate to one of the variables that affect the tool temperature. And then with that, we put those into a Simulink model and be able to create a system that could predict the tool temperature based on the three control variables. And then this will show you how we derived it.
Yeah, so first we derived an equation to model our process here, and that's in order to have an FOPDT model and find the tuning parameters. So the first steps was to do a first order plus dead time equation for the three variables. Then we took that differential equation into the Laplace domain, as you can see in this step right here. And then from there we divided over the tau s plus 1 after doing a little bit of algebraic manipulation there. And then we inverse Laplace it to get the final equation that we put into our Excel file. So that was, this is tool temperature at time plus 1 with respect to the three variables, and the time value.
The tool temperature of the previous time.
Yeah, the tool temperature at the previous time, sorry. And so from there we did a solver, and we solved for these three variables in order to minimize the sum squared error between the measured and model values, and found these four different sets of KPs and taus for each test. And so from there we took the average of each one to find, and we actually found that they were quite close. So after taking the average, we had those four average tuning values, and here's just a model of what, or an example of what our graphs look like. And you can see the blue is the model and the red is the measured, and they fit quite closely.
And with 5 sets of data, but we threw out one because the numbers were quite off compared to the other 4 sets. So that's why I only have 4 on the table. And so we built the Simulink model in order to see how well our KP values model our tool temperature. So we have 3 variables instead of 1, and we treated 2 of them as disturbances with feedforward controllers. So I took the KP values and the tau values, which we only have 1, into the transfer function, which is KP over tau s plus 1. So we have our KP1, KP2, and KP3. And with our PID controller, we just used a PI controller, and we took the P value as 1 over KP1, and our I values as our P over tau. And in order to model it like how the process does, we have ramps for our temperature, set point temperature, and our z-force. And for our speed, we just use a constant speed.
So in conclusion, we found that spindle power was the major variable that affected tool temperature. We saw this through our model, and we also saw it through the KP values. It was but 2 or 3 orders of magnitude larger than the other KP values. and it was the major variable in controlling tool temperature, as we suspected because we had discussed that with Scott. And we also found that friction stir welding can successfully be fit with an FOPDT model. Originally we were planning on doing a second order if it needed that, and we saw that the first order model fitted very nicely. As you can see in these graphs, here are our set points, and there's what we actually obtained. And so this is what we used from just straight from our Excel, and then we adjusted it slightly over here and got a slightly more aggressive control. And so either one would work. It just depends on the application you're looking and like the desired result. So from there we found that we can actually minimize the disturbances from z-force and x-velocity because we've found their Kp values, and we can model them, and then we would do the G3 over G1 negative to find the feed-forward control, and then you can actually go into the model, change your z-force, ramps, and x-velocity to new values that you maybe haven't tested in actuality, and with friction stir welding, you can kind of predict what would happen if you did have those values. So it is a useful addition to the model.